Hello. Since recently, I'm learning Linux BPF, Berkeley Packet Filter, and I noticed an article talking about BPF vulnerability. So this is a CVE number, and so like in this function, so this function has a vulnerability that can create a local user to privilege escalation to root user. So say, for example, here, um, so I have a Ubuntu virtual machine. So I log in as a local user, Vincent. So this is not a root user, but I can do a privilege escalation to root user with this code, this exploit code from the internet. I downloaded. So if I run this program, as you can see, I get a root prompt. As you can see now, I'm a root user. I can do anything I want on this virtual machine since I have the root account now, right? So and so this article explains how the what is actually the security vulnerability. So yeah, this is a good article to read it through, but I'm going to show you the code and to see how this security bug is. So in order to do that, let's open the code, the exploit code. So this is a part I'm interested. So first, this program will it is a BPF code written in BPF bytecode, and so this is the instructions. This is the array of bytecode instructions, and you notice that the first instruction is this macro, and which is disable the BPF verifier. So when you run a BPF code, first the BPF code, for security reason, the BPF code has to go through the BPF verifier to make sure your BPF code is safe and it's not it cannot randomly write random kernel memory. So the BPF verifier's job is to make sure your BPF code is safe to run in the kernel. But the irony here is for this security issue is the BPF verifier itself has a bug, has this security, and so right. So I'll explain how the BPF verifier failed to verify the BPF code. So this is the exploit code, and then the first couple of instructions. So this is the 4 instructions for the exploit to start. The first instruction is move 32-bit move instruction. So move this integer value FFF to register R2. So let's look at this. Look at this instruction. Okay. So this instruction is it's defined here in the exploit code. It says basically to move this immediate value. This is a constant immediate value, which is the FFFF to the destination register, and so the opcode is a combination of arithmetic logic unit and a move and a K. So that's the opcode. And so let's look at the verifier, how the verifier validate this instruction. Let's go to the kernel BPF verifier code. So this the do check is a function to do the BPF instruction verification. So it started with infinite loop. By the way, we can look at what a instruction BPF instruction structure look like. So this is a BPF instruction structure. As you noticed, so this is the first first byte is opcode, and you notice the last one is the immediate constant value, which is signed, right? So pay attention here. This is a signed immediate constant. So let's come back to the do check function and to validate all the bytecode. So here is what we want to look at it. So the opcode is grouped in a class. So so this is opcode we want to look at it because move 32, right? We want to look at this instruction. So the opcode is BPF ALU, BPF move, or BPF K. So this is in the do check function. This is where it started to check this BPF ALU or BPF ALU 64. So since we are 32, move 32, so we look at this, and so the function next is to check ALU up code, right? So this is where the CV mentioned. This function has a security flaw, and let's look into this security flaw in this function. So it has some stuff here, and we want to look at the opcode to be here. Yeah. So this is a code section we want to look at. So here is basically check the opcode, the source code opcode is BPF X. So X means to move a source register value to a destination register. But our instruction here is we are BPFK, right? So BPFK is to move the immediate value to the destination register, and okay. So here so here is if it's a BPF X, it's move a source register value to destination register, and but we are using this one, which is BPFK, to move this immediate constant value to destination register, and that's where so we doesn't match this if condition. We should instead come to this condition, which is assign this immediate value to the destination register. And here is the actual function to move this immediate constant value to the destination register, right? So because last time we checked the instruction immediate value immediate is a signed integer, and but if we look at this function here, the mark rec loan, and here is unsigned 64. So we are giving this function a signed integer, ffff I mean like 16 oh no, yeah, no, 8f, and but this function is unsigned 64. So you need to, there is a implicit signed conversion to 32 signed integer to unsigned 64 integer. So when you do this conversion cost, I think this article mentioned here, it says what will happen is yeah. So what happens when convert a signed integer to an unsigned one? According to this link documentation, the conversion will be this. So says the signed integer in this case is the ffff, you know, the number of f. It's okay, yeah. So this 8f 32-bit, and the actual value is -1 in decimal. So signed 32 integer. This signed 32 integer. This is actual -1 in decimal, right? So when you have this -1 here, and the actual value becomes conversion, this unsigned maximum 64-bit, right? So basically this this register R2 get the value of unsigned maximum 64-bit value, which is 8. You put 8f before this 8f, which is basically a sign extension, because the For signed integer, the first bit, one, meaning is the signed bit extension for two complement system. The first bit or most significant bit is the signed. If it's yeah. So anyway, so this register value are to get the maximum 64-bit value. Okay. So now let's look at this instruction. So this instruction is to compare this value with this unsigned 64-bit maximum bit value, right? So let's look at this instruction. So this instruction is like it's a like opcode is jump instruction or the BPFK opcode. So let's look at this how this instruction is validated in the BPF verifier. Okay, so we go back to the do check. So this is a do check infinite loop. We did this BPF bad code validation, which has a security flaw in this function, right? And so now the second instruction is start with jump. So this is a jump opcode, and since it's a BPFK, and so we will eventually come to this function, check conditional jump up, because the previous is not checking it's not a validate the BPFK, it's other opcode combination of a jump, right? So the last one is to check the condition jump up. So this is the function, check conditional jump. So in this function here, we want to look at the BPFK opcode. So you notice that here is we're checking the BPFK, and so combination of either BPF jump equal or jump not equal, and these are other conditions. So this is the so those are AND condition. So this is the part we also pay attention here. This is a function to compare the instruction immediate value to the destination register value. So in the previous move instruction, we already know that this is a unsigned. This register has the unsigned maximum 64-bit value, and so this instruction immediate is assigned 32 integer value. So let's look at this function. And this function defined here is, so the B parameter is also unsigned 64. So when you run this function, the compiler will also do the implicit of signed 32-bit to unsigned 64-bit conversion which will do the exact same conversion. The FFFFF number 8 of F will be converted to maximum 60 unsigned 64-bit value, and so this will be always true. So this will be true, right? So if this is true, and but we want the code is jump not equal to, right? So we are not doing this condition. Instead, we come to this branch. It's called a follow through branch, and return 0, right? So return 0 means the verifier, the do check function return once it returns 0. The BPF verifier will finish the BPF code validation. So that's the problem here. That's the problem here. So basically, this register 2 has after do this the conversion of signed to unsigned. This value always equal to this value because the signed extension. So if this is true, it will continue to run these 2 instructions. So what is this 2 instruction? This 2 instruction meaning return the move 0 to register 0 and exit the instruction. Basically, is to finish that. Okay, that's all the instruction needs to be run for the verifier. Right? But if this, but when so one thing I have to mention is when you load the BPF instruction bytecode to the kernel, so the BPF will emulate emulate the code and run it virtually. So the verifier, since the verifier itself has bug here, it only sees, oh, this condition is true, and yeah, that's all. Then finish it, exit the instruction. But when the BPF code is actually run by the kernel, this condition will not true, and it will not true. It will jump 2 instruction. So which means we'll skip this. It is another branch. We'll skip these 2 instruction, and come here. Come here to continue this instruction, which is started to exploit the kernel memory. So I can show you when that code actually run. I think it's run in this. If I BPF core run, I remember, yeah. So this is actually when the bytecode gets to run in the kernel, and here let's look. So here has the like for the first move instruction, like notice here the 32-bit move. You notice this thing. It will first do a unsigned 32 cast. So cast this signed 32 integer to unsigned 32 integer, then assign it to the destination register. So that's the correct way to do it. Instead of in the BPF verifier, it's just signed. It's did signed 32 to unsigned 64 conversion. So it means when the kernel actually run the code, it's different than the BPF verifier emulation code. So like you have a bunch of instruction code uh, uh, skipped by the verifier and run in the kernel and started to read write random memory. And so I hope yeah. So let's look at the. So the following is just exploit the kernel and basically it's attached the BPF code to a socket and then get the current task address. And yeah, we can explain how the exploit actually works in detail next. But this section we only like want to see how the security, where the security flaw is and why it is a security flaw. And so again, this is a good article from the medium.com, and probably explains better than me. And but I just want to do a live demo just to show you the exploitation. Okay, thank you.